Okay.
Well, thank you. Thank you for inviting me. Thanks for coming. It's really interesting to just see what Lean Startup is doing in software. I'm a hardware engineer. I'm a mechanical engineer, and I design electromechanical devices from concept through production in the medical, industrial, and consumer products industries. So I want to talk to you about how I use rapid prototyping and prototyping techniques through the new product development design process. So it wasn't long ago that engineers had very limited resources for creating prototypes of plastic parts. You could make a clay or foam model in a matter of days. It's very cheap and easy to do, but it's not very functional. You can't use it and test load capacities or even mechanisms. But then you could make a machine part out of a plastic, machine plastic part, and it's pretty functional. Costs a little bit more. It takes maybe a couple of weeks to get that part back, but it has to be pretty simple. If you want to do something with overmolded rubber or a live hinge where you have one plastic part that bends on itself, then you're going to be talking about months of development to create the tooling and maybe tens of thousands of dollars. So it was very difficult to create prototypes. It was expensive and it took a long time. So there wasn't much prototype iteration before you got into the production cycle. So now there's 3D printing. There's a wide variety of 3D printing techniques, SLS, FDM, SLA. I mean, I won't go into all the acronyms and what each are, but the advantage is that you can get prototypes of a wide variety in real materials, nylon, ABS, even metal in a lot of cases, and you can get them for very, very short time, in a matter of days, and you can get them for a very low cost. It's very cost effective. You can get things like nickel-coated SLA, which is plastic. It looks very nice and it actually increases the strength. You can get FDM, which is a part that I actually made. So kudos to the CCBC Fab Lab. I got this made today, and it's it's something that I can actually use and it has a lot of the properties, the physical properties of a ABS part. So let's try not to break that, but you can pass it.
There's only one.
So you can.
And he needs it.
Right. So what this means is you can get a lot of prototypes, you can do a lot of iteration, and you can learn a lot about your design before you start really production. So the iteration is extremely important because with each successive cycle, you're learning about your device, or your product. You're finding out things you didn't know. You're testing concepts that you weren't quite sure about. So you're able to really learn with each step. So you can design, then you prototype, you test, you refine that design, you build it again, and you repeat it until you're confident with what you're working on. So here's something that I was working on. It's a handle for an espresso tamper, and we wanted to make it out of concrete. It would have a nice feel, nice weight to it, an ergonomic handle, and a warm texture that would make it useful in a professional setting or a consumer kitchen. You can put a custom logo on there for a business or personal as a gift or a family reunion or something like that. So I designed the product, and then I also designed the casting mold so you could pour the concrete into it. So I wasn't sure how the handle would feel in my hand. I mean, I had some guesses, but so I built a prototype. This prototype cost about $25 and it took 20 minutes to build. It's mostly hollow, and that's one of the advantages of FDM is I can make it really hollow, and then I can take it and I can sand it and I can shape it until it feels just right, and then I go back and I modify the design so that that's the new part that I'm going to make. So in addition, I learned, or I realized that the single cavity mold was going to be really difficult to get the quantities in production. So when you are making a concrete part, you mix and you set up the concrete and then you pour it, and so each time you do that, that's the same amount of work. So why not make 3 of them instead of just 1? So you can triple your output with just a little bit more material for the mold. So I built the mold, and this is actually built out of 3D printed technology. This is FDM mold with some polyjet components for the logo because it has a much better resolution. And then my manufacturing partner built the first units with pretty good success. So you can add customization like dye, or you can add fine glass particulate to really customize the surface finish once you're done. So even though we made the first units, I'm still thinking about how I can improve the process. So this is the part where there's logo customization. So if I want to make a custom logo, my goal is to make it as inexpensive as possible so that I can tell someone, oh, you only have to make 4 before you can get a custom, you can get a custom logo, and I can throw it in there if you buy 4 or more or something like that. So I tried to make it smaller and thus less expensive. So I took the logo and I made that a separate small piece, and then I took the base that I had, which was connected, and now it's a piece of laser cut acrylic. So it's much cheaper to make. I could also make that down in the Fab Lab, and it's very easy. I can interchange the parts now because there's just a screw, so I can throw them in and out of the drawer, whatever, and add it. So I also wanted to talk about another case study. This is for a medical device. So I had a lot of images for that product, but I wanted to talk to you about something that had a lot more prototyping and a lot more that we learned about. So this is a medical device that I was working on a few years ago. It's for a high accuracy hematocrit measurement device. And hematocrit is the measurement of red blood cells in your blood. So I was tasked with coming up with a way to draw the blood from the sample cuvette that you prick your finger and take the sample, put it in the device, and then draw that blood into the measurement area of the device. So let me show you a picture just to get something in your mind of. So this is one of the preliminary prototypes of the pump that after a few iterations, but not near the end. So it didn't. Unfortunately, I can't really show you too much of the design because of confidentiality, but it ended up going into this device, the UltraCrit from Separation Technology. And this is the device as it's sold today, and you can find it in certain blood banks. And just to give you an idea of what I'm talking about, the kind of device I'm talking about. So we started off with the idea that we would integrate an off-the-shelf component. So I'm looking at solenoids, I'm looking at micropumps, and everything is much more expensive than we're looking at. We have a very tight budget, and it also requires a lot more power than we like to give. So the device is a handheld device, it's battery powered, so we have a very tight budget, and we also have a very tight power budget. So I want to create something that is it's going to meet those needs. So I'm thinking about alternatives, and one day I'm standing in the hallway talking with a few electrical engineers, and they start talking about this shape memory alloy wire that they got from a sample kit. And the wire's cool. You put current through it, it heats up the wire, and it causes it to shrink 3 to 5%. Now, the really cool thing is that it's very strong for its size. So you can use it in an actuator, and they provided a very simplistic actuator, and then you stretch it out and you just keep doing it. And it can last forever under the right circumstances. So I take the sample kit back to my desk, and I start thinking about how I can use this to move blood around the device. So this is actually something that starts to work. I'm creating concepts, and I'm building prototypes, and I'm building a lot of prototypes. So I'm able to make parts. I put the plastic parts together. I use SLA, I use cast urethane, I'm machining metal inserts, I've got some off-the-shelf springs thrown in there, I've got an injection molded diaphragm to move air around, and I've got a few neodymium magnets, because what complex device would be complete without some magnets? But the shape memory alloy wire turns out to be extremely delicate. It's very sensitive to temperature, to bend radius if you put it around a curve to actuate and to bring something closer. It's sensitive to the air cooling, convection cooling. It's sensitive to the return force of how to stretch it out once you've contracted it. All these factors were adding up, and as I would solve one problem, I would identify 2 more that I hadn't thought of. So it was becoming a very complex product development cycle. So the advantage of being able to use rapid prototyping to really turn, to get prototypes quickly to get prototypes turned around quickly, to send out prototypes that were maybe multiple versions or to have a slight variation on them, and I could get those back and I could test a concept quickly, I could fail quickly, and I could move on to the next stage. So the prospect of this pump was really, it was the low cost, low power pump was really compelling, and we were starting to make progress, so we kept at it. But one thing that was really interesting was you have to know when rapid prototyping is insufficient. So we were really going with the rapid prototyping, SLA and cast urethane, and we learned we were having some inconsistent data, we were having some intermittent failures, and we were starting to see that the thermal instability of these materials was causing problems. So at some point, I would recommend that, one lesson that we learned that we didn't know quite in time was that I would recommend that at some point you might look towards production techniques to really, if you're going to test put the design through its paces. So you want to really understand what it is that you're working with before you start to really do environmental testing and things like that. So eventually we understood how to use the wire without overheating it. We were able to ensure accuracy and reliability. We were able to manufacture it and integrate it into the design. The total project took about, I guess I'd say, the better part of a year, and we must have gone through hundreds of prototypes. It turned into much more of an ordeal than we'd ever originally suspected. But the sound of the clicking pumps going through 1 million cycles during life cycle testing off in the corner of the office really helped to validate that the effort was worthwhile. So, and now it's for sale, so thank you.
One question?
Because we're running behind again.
So this design process took a lot longer, I'm guessing, than you thought it would? Or did you end up coming in within budget on time?
No, I was never given a budget. The unit cost was the budget, not the development. And I'm reviewing my progress with the project manager. So every time he's saying, "Wow, this is going over budget," but you can see that it's getting there. You're making progress. You can see the end of the road, and there's a lot of hurdles up ahead. But what's the alternative? And so the alternative was spending 10 or even 20 times more for a solution that could work, but it was not ideal. And we could really see this going forward. So it really had a lot of advantages, and it was difficult to make that decision. I'm glad I didn't have to. Right. So I was being told sort of keep going, and I was saying, well, I think I can get there. Let's keep going.
The transparency and the interim results.
Exactly. I didn't just go away for 6 months and come back and say, here's, yeah, exactly. It didn't work, or it did, and here's your big bill. So.
Was the alloy nitinol?
It was nitinol, yeah. That's pretty good guess.
Great. Well, thank you very much.